In this video, we're going to talk about the ideal gas model, but you should go back to the previous video and definitely watch it first in order for you to be able to understand this. Otherwise, it's not going to make a lot of sense because we're going to be talking about something called the compressibility factor, which I've explained previously. And, well, if you're joining me after watching it, well, then you would know that compressibility factor is given in terms of pressure, specific volume, and specific gas constant R, and temperature of the gas. So what we say is that as if, let's say if the pressure of our gas is really small, it's relatively small, let's say it's really, really small, it's a lot smaller than the critical pressure for the gas, or let's say the temperature of the gas is a lot higher, it's much larger than the critical temperature of the gas. So either this condition is being fulfilled or this condition is being fulfilled, or maybe both these are being fulfilled together. And what happens is that this compressibility factor here, this approaches 1, this is approximately 1, and if this is approximately 1, then we can, with reasonable accuracy, say that this is actually going to be equal to 1. So at such states, at states where z is equal to 1, you would basically plug that into this equation, and what you will get is that PV is equal to RT. Okay, so we've got PV is equal to RT, and this is a really important equation. It's called the ideal gas equation of state, and you usually deal with it a lot when you're dealing with thermodynamics or fluid mechanics. So this is the ideal gas equation of state in terms of specific volume and in terms of the specific gas constant. If you were to convert it into a relationship for the universal gas constant, then basically you're going to change it, and instead of specific volume, you're going to be using volumes, capital V here. It's going to be equal to N, which is the number of moles of the gas, and R dash is the universal gas constant, the value for which we usually know, 8.314, and you can check what the units are for that. And so these are two different forms of the same equation. And this is what the ideal gas model is based on for states where z is equal to 1 and where PV is equal to RT. What we also from this equation find out is that the specific internal energy depends only on temperature in these instances. In such cases, it only varies with temperature too. And this is based on experimental observations. So we've got PV equal to RT, and we are saying that internal energy is depending on temperature only, so it's going to be a function of temperature only, and if it's a function of temperature only, then enthalpy is going to be a function of temperature as well. And I could write enthalpy in terms of the internal energy, which is going to be UT plus RT. Basically, we're using that same equation where we saw that H is equal to U plus PV, pressure into volume, and I've just substituted, instead of pressure and volume, I've substituted RT from here, and well, this is only based on temperature. So these three equations here, these three equations all together comprise of what is known as the ideal gas model. Okay, this is how it's summarized. And well, I mean, the specific internal energy and enthalpy of the gases, it depends on two independent properties, usually not just temperature as we see here. So evidently this is a huge assumption on the part of the ideal gas model. Um, so whether you should use the ideal gas model or not, it basically depends on the error that is acceptable to you in a given calculation. Gases usually do not approach ideal gas behavior, and this is a huge simplification. And it's also basically another simplification is that it's only applicable where z is equal to 1. So it's better if you use uh, tables instead of using the ideal gas model, because this doesn't really give you accurate data. But if you're okay with a little bit of the error that you're going to find by using this model, well, then you could use this too. So I'm just going to move on and show you an example, and we're going to just look at that example and try and solve it based on the ideal gas model. So I've got, let's say, a piston cylinder arrangement, and a thermodynamic cycle is going on, which has 3 different processes. I've got the initial state given to me, state 1, at which I've got a certain temperature, and I've got pressure given at that state 2. At state 2, I've got only pressure given to me, and I have to basically find out the temperature at state 2 and the specific volume at state 3. So in order for me to make the PV diagram sketch, first of all, let's say I've got this PV diagram over here, pressure on the y-axis, volume on the x-axis, and what I already know is that I have isotherms on the PV diagram. Because I'm looking at air, and it's a gas, so then I'm going to be dealing with the gaseous part of it. So let's say this is one isotherm, which is at temperature of 30 degrees. Okay, and now the second isotherm is going to be, let's say, somewhere here, but I don't know what it is because I need to find out the temperature at state 2. So I've got process 1 to 2, which is a constant specific volume process. Okay, so constant specific volume means, let me just change this a little bit. Let's say this is the isotherm. So constant specific volume means that it's going to be a process from 1. Let's say this is state 1. So it can be a process like this, straight up. It's a vertical. There's no change in the specific volume. That's why it's state 1 to 2. But you do not know the temperature at state 2 yet. Maybe the temperature is lower than 30 degrees, then you would have to go the other way around. Then that's going to be over here. But let's just assume that this is how it is right now. And what I can do is that from the ideal gas model, if I have to find out the temperature at state 2, let's say, then it's going to be T2 is equal to pressure at 2, specific volume at 2, divided by R, which is the ideal gas. And, well, I do not know what is the specific volume here, but what I do know is that V1 is equal to V2 because it's a constant specific volume process. So V1 is equal to V2. From here, I can write V2 in terms of RT2 by pressure at state 2. And what else can I do? Well, if I'm writing the specific volume at state 1, that would be equal to RT1 divided by P1. And because V1 is equal to V2, so that means that this is going to be equal to V2 as well. And what that means is that I can just equate this over here to this one, and R is going to cancel out. We're going to be left with basically T2 by P1 equals T1 by P1, and I'm just going to take it to the other side, so I'm just going to write it in terms of P2 by P1 into T1, right? Because I'm equating this to this. It's going to be equal to T1 by P1 is equal to T2 by P2. P2 is going to go onto the other side. It's going to be P2 by P1 into T1. And I know what the pressure is. It's 2 bars at state 2. I know what the pressure at state 1, it's 1 bar. And I know what the temperature is. So the temperature is at state 1, which is 30 degrees Celsius. It's going to be 30 degrees Celsius. So temperature at state 2 is going to be equal to 60 degrees Celsius. So my assumption was okay, it was correct. It's somewhere here. This is an isotherm that is at 60 degrees, and that is where my state 2 is. So the process 1 to 2 comprises of state 1 to 2, and the process 2 to 3 is a constant temperature expansion. And expansion means that specific volume has to increase, right? It has to increase. So that increases in this direction, but it's also a constant temperature process. So this is the isotherm. This is the constant temperature curve. So I have to go from state 2 to state 3 in this direction in order for me to have, let's say, constant temperature expansion. And then it's a constant pressure compression from state 3 to 1. So that means I have to keep on expanding this. Let's just make it like this. Let's change this curve. This is over here. And let's say from 2 to 3 I'm moving on this curve. And I get here somewhere. This is state 3. Because from state 3 to 1 it's a constant pressure expansion. So we need to have a horizontal line here in order for us to have constant pressure. It's compression, so that means specific volume has to decrease. It decreases in this direction. So this completes the thermodynamic cycle for us. Okay, this is the PV diagram for us now. And what else can I find? I have to find out the specific volume at state 3. So I could do that by writing again PV equals RT. I could just write specific volume at 3 equals RT3 divided by P3 over here. Or I could substitute instead of the specific gas constant here, I could just use it in terms of the universal gas constant divided by the molecular weight into, well, instead of using T3 and P3, I'm going to use, what am I going to use? Let's see. I've got T3 is equal to T2 given to me from here, right? Temperature at 2 and temperature at 3 is equal to each other. So that means I could just substitute, instead of T3 here, I could substitute T2 here because I already know what it is. And instead of P3 here, because it's a constant pressure process, so pressure at 3 is equal to pressure at 1. So I'm just going to use P1 over here. I already know what it is. It's given to me here. And, well, R dash is going to be equal to R8314. And the molecular weight, I can go to Appendix A1 and find out what the molecular weight is for air. It's going to be 28.97 if you go and take a look. Appendix A1 in Shapiro's book. And just multiply it by the temperature. Make sure that you convert the temperature into kelvins to keep the units consistent. It's going to be 60 plus 273 kelvins. And you're going to divide it by pressure at 1, uh, which is, let's say, 1 bar, so you have to convert it into pascals, let's say. So you just do that, plug it in here, and you're going to be able to find out the specific volume in terms of meter cube per kilogram. So this is how you work with the ideal gas model. Now I'm going to leave you with a question for you to just solve it yourself and see how you can do that. I'm just going to explain how you can do that. You've got a container, a tank, in which you've got a certain volume of nitrogen available to you at a certain temperature and pressure. And what you have to do is you have to find out the mass of nitrogen, and you have to do it by using, first of all, the ideal gas model, then use the compressibility chart data. From both of these, find out the mass of nitrogen. And once you do that, then what you have to do is you have to just assume that the value that you got from the ideal gas model is not as accurate as it is from the chart data. So you're assuming that this is 100% accurate. There's no errors in the value that you get from here. And from that, you have to figure out how much of an error you found by using the ideal gas model and the value of the mass of the nitrogen. So that is something that I'm going to leave up to you. This over here, it could be, you could change it. This could be in terms of x, let's say x meter cube, and this x, then you could play around with it. Instead of substituting 0.05 meter cube, you could have, let's say, 0.03, 0.02 meter cube. So this is x over here.